All right, so we're taking a look at acceleration just to get ourselves thinking about this. An acceleration is a change in velocity per unit of time. And so really what we're looking at with acceleration is velocity changing and how much time does that take. So there's lots of different scenarios. We're going to talk about some of those today. And then we'll get to an equation and help you kind of get set up to solve some of these. One thing we do want to point out that acceleration, we should add that to our list of vectors. So a little star next to that. This is a vector. It will require a direction. Usually with accelerations in physics, we talk about it being either positive or negative. So in the positive direction or the negative direction, and that ends up taking care of our direction that we need. But just remember, if you are solving an acceleration, make sure you put some kind of a direction. Just like if we did velocity instead of speed, if it asked for a velocity, then we needed to include a direction. That kind of is what this is all about, is seeing that this is a change in velocity, and we know that velocity is a vector. And so since it's a vector, acceleration is also going to be a vector. It's going to be taking place in a very specific direction. All right, so vector quantity, check, we got that. Here's some of the scenario kind of things. An acceleration can be positive, it can be negative, it can be zero, and I just want to kind of talk you through those. A positive acceleration typically means something is going forwards and it speeds up. So this could just be a speed up. So I'll write that down. Speed up. So you're in your car, the light turns green, you step on the gas pedal and you speed up. That would be a positive acceleration. Negative acceleration could be a couple things as well. Negative acceleration could mean that the object is slowing down. I'll put slow down. So same thing, driving in car, but you hit brakes this time. Your velocity changes and you slow down. That's a negative acceleration. But it could also mean that the object's speeding up. Now, these would be different scenarios. This would be one scenario. The other scenario would be if the object speeds up going backwards, then it would be a negative acceleration as well. So I'll put speed up backwards. I'll put speed up back. That would be an example of a negative acceleration as well. So this is you in your car, kick it into reverse, and you speed up, but you speed up going backwards. That's a negative acceleration as well. So there's two scenarios there for that one. Also two scenarios for zero acceleration as well. I think the most obvious one is an object that is stationary or at rest. It is not accelerating. So we could put that. The other one that's a little bit harder to think about is like cruise control. What if you're going at a constant velocity? Constant speed, I'll put. Constant speed or a constant velocity, if you think about it, cruising at 70 miles per hour, is your velocity changing? And the answer is no, and that's the way we defined acceleration, as a change in velocity. So if you're in cruise control example, then you're not accelerating. And so we would say you have zero acceleration. So those are some of the key scenarios here for acceleration to think about. One other thing that we want to add here is that a change in direction. Change in direction is also an acceleration. Think about it. Velocity has a direction, right? If you change that direction, you change velocity. And if you change velocity, boom, you just changed acceleration. Or you just accelerated, you changed your velocity. So a change in direction is acceleration. So you could be going the same speed, 70 miles per hour, but all of a sudden you go from driving to the west to driving to the north, you accelerated. So change in direction is an acceleration. So keep that in mind. The units for acceleration, so we'll put that on here. The units are meters per second squared. If you're given a problem where you have to convert stuff, I would recommend keeping meters per second squared and converting other things. Like if you're given velocities in kilometers per hour, convert those to meters per second so that it works with your acceleration in meters per second squared. This is tricky to convert because that unit on the bottom is squared. It's totally doable, and if you know what you're doing, feel free. It's usually easier to leave this unit alone, keep it in meters per second squared. Just a brief talk about what meters per second squared means. If we rewrite that like this, meters per second, this I think really helps define this unit. Right here is velocity, right? Meters per second. And acceleration is the rate at which this changes per second. So the rate at which velocity changes per second. And so sometimes you'll hear meters per second, which is totally a totally fine unit to use. And we just kind of simplify that down to meters per second squared. So that's where that comes from. Okay, let's look at the equation. Here is the equation, which makes sense based on what we've talked about so far. So if we're solving out acceleration, here it is. New characters pop up. So we've seen velocities before. So the V's and the T are common. We've seen that happen before. The VF is new. So this means final velocity, and VI means initial velocity. And so the way that I program that into my brain is I say, okay, how fast was the object moving at the end of the problem? How fast is the object moving at the beginning of the problem? That's VF and VI. You want to make sure that you get those in the right place, obviously, so be careful. If you have to rearrange this equation, I'm going to walk you through that. What if you have to solve for T, which would mean we need to get T by itself, which involves us moving T to this side and then shifting A across. So I'm going to multiply both sides by T and then divide by A. So here's what we would get. Basically, if you're solving for time, the A and the T just flip-flop places. So I multiplied by T, and then I divided by A to get time by itself. If we had to solve for, let's say, final velocity, so this guy right here, I'm still going to multiply both sides by T. So I'm going to get AT equals VF minus VI. I'll do this, step this out. It's a little, not really more complicated, but a little less easy to picture. And then all you have to do to get rid of VI, since it's subtracted here, is you're going to add VI to both sides. And so I'm going to make a spot up here for that. So I'm going to go to AT plus VI, add that to both sides. There is final velocity by itself. And then the only other possible thing that you could solve for out of this equation would be initial velocity, which would be this guy right here. And so I'm just going to use this form of the equation to rearrange that. I want VI to stay, and I want to get rid of AT. And since it's added, I can just subtract both sides by AT, and that'll get VI by itself. So I'm going to have EF minus AT. So in terms of the rearrangements, you have this, and then you have these two guys here. So there's three different ways to possibly have to rearrange that equation when you go to solve out the problem.